Hi, in this lecture, the third part of the topics on the field effect transistors is introduced. By this slide, we start discussing the current biasing of MOSFET devices. Actually, we can implement a current source by using MOSFET devices. The given circuit can be considered as a first step for such a design. Let us clarify the operation of this circuit by the following example. Based on the given parameters of the NMOS current mirror circuit, we need to determine the bias current IQ1, the gate to source voltages of transistors, and the drain to source voltage of the transistor M1. Let us first focus on the transistor M3, which is biased in the saturation region since the drain terminal is connected to the gate terminal. Its drain current, ID3, is equal to the independent current source IREF1. By this equality and using the current expression, we can obtain the gate to source voltage. The transistor M2 is assumed to be biased in the saturation region. Since the gate terminals of M2 and M3 are connected to each other, the gate to source voltage of M3 is equal to the gate to source voltage of M2. Then the current ID2 or IQ1 can be found. Again, M1 is assumed to be biased in the saturation region. Then, by using the current IQ1, the gate to source voltage of M1 is calculated. Since the gate terminal of M1 is connected to the ground, its drain to source voltage can be easily found. And the saturation region assumption is verified. As you realize, the current IQ1 is equal to the independent current source. In other words, since the parameters of the transistors M2 and M3 are equal, they reflect or mirror the reference current value. However, by changing the transistor parameters, we can adjust the reflected current value. The constant current source can be implemented by using MOSFETs, as illustrated in the slide. The transistor M2 is assumed to be biased in the saturation region. The resulting gate to source voltage on M3 is applied to M2, and this establishes the bias current IQ. Since the reference current is the same in M3 and M4, we can give the following. We can also write then the gate to source voltage of M3 can be rewritten. Finally, since the gate terminals of M2 and M3 are connected to each other, the current IQ can be expressed in terms of the gate to source voltage of M3 as follows. In the example, based on the given transistor parameters, we need to determine the currents and voltages in the MOSFET constant current source. By using the expression just derived, the gate to source voltage of M3 and the current IQ at the right branch can be found. This current also flows into the transistor M1 and the gate to source voltage of M1 can be also given. Then the drain to source voltage of M2 is calculated, and the assumption that M2 is biased in the saturation region is verified easily. In most applications, a single transistor amplifier will not be able to meet the combined specifications of a given application factor, input resistance, and output resistance. Transistor amplifier circuits can be connected in series or cascaded as shown in the figure. The overall voltage gain may not be the product of the individual amplification factors. There are many possible multi-stage configurations. We will examine some of them. Let us design such a cascade configuration based on the given parameters of the transistors and the required levels of the drain currents and the drain to source voltages. Let us first focus on the right part of the circuit and the second transistor M2. For this part, the resistor RS2 can be calculated. By assuming M2 is biased in the saturation region, its gate to source voltage is found and the saturation region assumption can be verified. Since the drain terminal is connected to the voltage source V+, and the drain to source voltage is given as 6 volts, the source voltage can be calculated. Since the gate to source voltage has been found, the gate voltage of M2 can be also given. Let us now focus on the left part of the circuit and the transistor M1. The drain voltage of M1 is equal to the gate voltage of M2, just calculated as 1.78 volts. Then we can easily give the resistor RD1. The source voltage of M2 is calculated. Then, based on the voltage of the source terminal, the resistor RS1 is presented. By considering the saturation region for M1, its gate to source voltage is calculated. Then the gate voltage is given. The same current flows into the resistor R1 and R2. By considering the gate voltage of M1, we can write the following. Then, using the input resistance Ri, R2 can be easily found. And finally, R1 is given. Let us have another configuration, namely Cascade configuration, for which we will try to design the circuit to meet the given design objectives. Let us first focus on the source voltage of M1. Through the saturation region assumption, the gate to source voltage of M1 is given. Then the gate voltage of M1 is written. By employing a voltage divider, the gate voltage can be rewritten and the resistor R3 is found. Similarly, we can determine the source voltage of M2. Since the parameters of the transistors are the same, under the saturation region assumption, the gate-to-source voltage of M2 is the same as in the M1. Then the gate voltage is calculated. By employing a voltage divider, the resistor R2 and then R1 are found. Finally, the drain voltage of M2 is given, and the drain resistor RD is calculated. This is the last slide of part 3.